Okay, so for today, being Class 1, Unit 1 and 2 focus, we're going to basically be doing a review of the Unit 1 and 2 applications of differentiation. So this will be your tangent line, normal line, and how you find stationary points. A decent number of you have been to enough of these practices to where we have done a decent number of these concepts and applied them already. So I'll go through the stuff fairly briefly. If I'm going too fast and this is your first time looking at these concepts, feel free to ask me to slow down. I'm more than happy to dive into the concepts in more detail. But if we're all already familiar enough with it, then for the most part we'll be aiming at some of the harder questions where you actually apply these concepts to, well, those harder topics. But okay, so tangents and normals is the first applications of the derivative. What is a tangent line? A tangent line has to meet the following criteria. Basically, it is a line that brushes up against the side of a function, and what that basically ends up meaning is that it needs to share a point that the function shares. So both f of x and the tangent line have the exact same point, in this case 1, 1. And the last criteria there is that the gradient of the tangent line has to have the same gradient of the function. That's what makes it brush up against the side. The gradient of f of x and the gradient of the tangent are identical at that point in which they intersect. So with those criteria, you are fundamentally finding a linear equation, and so the gradient point formula, or otherwise, y equals mx plus c, these are going to be your friend in solving these particular questions. The bulk of the challenge is going to be in finding the gradient of the tangent line, because we already know how to find intersection points, right? It's just a matter of either equating the two curves together, or if you have an x, you sub in the x into your function to get the corresponding y. Finding the coordinates not usually the issue. What's usually the issue is getting the gradient of the tangent line, and there are three main ways that you can typically go about it. The main way by far is going to be finding the derivative. Derivative is all about finding gradients. So if you find the derivative of your original function and you shove in the x coordinate at which you want to evaluate the gradient, you will get the gradient. The other two, well, this next one up is more of the question where it's tangent line adjacent in the sense that you have 2 points that the tangent line must pass through. This technically isn't any different to just having 2 points for any given linear, but what you'll find is that the questions that use this often will require you to find 2 separate ways of finding the gradient using those 2 known points. But yeah, basically if you have 2 known points, well, you can just do a rise of a run. What you'll often find, actually, well, I'll just save that for when we go through the example. And last is that the gradient is always equal to tan of theta, where theta is the angle in which the line makes with the horizontal, specifically in the anti-clockwise direction. This is positive theta, this would be considered negative theta. So make sure it's always going in the anti-clockwise direction. Pop in the chat or otherwise if anyone needs a refresher on why tan theta gives you gradient. Happy to dive into that if we need a refresher. Otherwise I'll just skip over it if no one mentions anything. Okay, example 1, finding the tangent line, just stock standard basic. This is a very standard question. You have your function, find the tangent at x equals something. In this case it's x equals 2. So what you want is the point and the gradient at that point. We already have the x coordinate, so a nice little starting point is to just get the y coordinate off rip, right? X equals 2, to get the y coordinate, shove that back into your original function. We now have the point. All we need to do now is find the gradient. There is very minimal information here, but whenever you have an f of x, you can always find your f dash, your derivative. And so that's what we're going to do here. To get our gradient, we're going to find the derivative of the quadratic. That's going to get us f dash x equals 2x using our lookup table of derivatives. From there, any x that we shove into this spot is going to give us the corresponding gradient. So if we want to find the gradient at x equals 2 of f of x, we shove x equals 2 into the derivative of f of x. When you do that, you get gradient of 4. we have the gradient, we have the point. You can now shove that in your gradient point formula. Or if you want, you can do the whole y cos mx plus c thing. Any questions there? Let me know. Otherwise, we will move on to the second example. And you can interrupt me at any point, that's perfectly fine. Here's one of the examples where you have two given points. So we have a tangent to the tangent to the curve with this equation at this point passes through the origin. So we're not given the tangent, we're just told that we're taking a tangent at a particular point and that tangent passes through the origin. This isn't really a question about finding a tangent line, this is a question about finding the value of a specifically. However, it's in the same area of study, more or less. You still need to know about tangents, or at least about linears. So, because we're given two known points, even if it doesn't explicitly look like a point, just stating the origin is in fact a point, 0, 0. So one of the first things we want to do here is try to get our gradient. We want to try and relate the information that has a in it into some sort of equation. And because we have f of x information and 2 points, we can get a lot of gradient related information. So let's go ahead and do that. Point 1 is there, point 2 is the origin. All we're going to do is a quick rise of a run, thus getting us gradient is equal to 2e to the 3a divided by a. That's one equation, right? We got m equals this. We have a in an equation. But we also have m, the gradient, in the equation. And that's not necessarily great. We want to get a on its own with a bunch of numbers, more or less. So the goal then becomes, can we find m, the gradient, in another way? And we can. Whenever we have f of x, the function, we can always find the derivative of that function. So again, looking at our lookup table for derivatives, derivative of 2e to the 3x will just end up being 6e to the 3x. And because we have the derivative, we can now sub in the point at which we are trying to find the gradient of. Right? It's the tangent at this point, not the tangent at the origin. Right? The tangent goes to the origin, but the point at which we're finding the tangent is this one. So we take this x coordinate of a, shove it in there, not much is really changing. You're essentially just replacing an x with an a. But what you have achieved is another equation that is equal to the gradient, both of which, if you compare to the rise of a run, you have m equals something with a, you have m equals something with a. Because they are both m equals something, you can make them equal to each other. Therefore, removing the m, you now only have a's in this equation. E doesn't count as a variable, that's a special number like pi. And then yeah, you just rearrange and simplify until you finally get your a. I did finish this one off to get the actual tangent, but technically the question only really actually asked for the value of a. If it then asked a follow-up of like, okay, now find the tangent line, well, you now are kind of a bit spoiled for choice here, because you have your gradient, you have a couple of ways you can find gradient actually, m equals that or m equals that. Plugging in a equals a third into either of those will get you what you want for your gradient. Or, and the other thing is, you only need 1 point, where you have the origin and you have a comma 2e to the 3a. So, bit spoiled for choice there. The easiest way to go about all of that would have been using the simplest gradient method and then just using the origin. The reason why we can use the origin here in this case is because the origin is a known point on the tangent line. You don't necessarily always have to use the point at which you're finding the tangent specifically. Technically speaking, because it's just linear at this point, you just need a point that exists on it. So this one is easier to use, 0, 0. Any questions so far? Let me know. Otherwise I'll keep steaming forward. Okay, next up, find tangent line given a function and an angle. So we got our function f of x, 45-degree angle, anti-clockwise from the x-axis. So we want to find more or less where do we have this 45-degree angle that is anti-clockwise from the x-axis? Whenever you have angle-related information, it's often the case that you can convert that directly, or it's often the case that it's required to convert that directly into gradient-related information, of which you just, plug into tan theta. Tan 45 will give you 1. From there, we have the gradient that we need. What we now need is the point. And if we look at the information that we don't actually have an x or a y. And that's a bit challenging. But what we do have is an f of x, and whenever there's tangent style questions, it's pretty much a given that as soon as you have f of x, just go ahead and find f dash. There might be a question where you don't need f dash, but it doesn't take a lot of effort to get it. Right, you're just doing the derivative of a polynomial like 9 times out of 10. So we have this statement f dash x equals 4x minus 3, or in other words, gradient equals 4x minus 3, and any x value that we shove in there will get us a corresponding gradient, or vice versa. Since we have the gradient of 1, that's what we're trying to force, we want to figure out where on the curve gets us a gradient of 1. Gradient of 1 goes in the gradient spot, the derivative spot. And by solving for x, you are essentially solving for what x coordinate on my function has that gradient of 1. In this case, you get x equals 1 as well. That gets us an x coordinate. All we're going to do is shove that back into f of x to get the corresponding y coordinate. This gives us x and y, that's our point, and our gradient. That's all we need to find the tangent line, so we plug all those information into where it needs to be, and you get the relevant tangent line. So to go back to the question specifically, it said find the tangent to f such that it makes a 45-degree anti-clockwise. The 45 degree was forced by gradient of 1 using tan theta, and the rest of the information to create the tangent came from finding what point had a gradient of 1. Any questions there? Okay, last up for tangents and normals, the normal line. This is effectively the same thing as I've just discussed. The tangent line brushes up against the side of a function. The normal line's ever so slightly different. The normal line intersects the point at a right angle. Do I have a picture of this? Really, I don't. Okay. Let me draw one. Okay. If we pop over to the handwritten bit, I draw some curve. This is my point. The normal line would intersect at a right angle at that particular point. That's all it is. That's what it is conceptually, anyway. As far as how you change your procedure, basically next to nothing. The only thing that changes is that the gradient of the normal line is the same thing as -1 divided by the gradient of the tangent line. So do everything as discussed already, but when it comes to plugging into your tangent line formula, instead of putting the gradient in that spot, you put -1 divided by the gradient at that spot. That's literally it. So all the exact same questions that were already discussed could have just as easily said the normal, and all you would be doing would be replacing the gradient with -1 divided by the gradient instead. We'll look at an example anyway, just to make sure that we're all on the same page. In fact, I'm pretty sure I use the exact same numbers as the first example that we looked at. We have the quadratic, finding the normal this time to x equals 2, at x equals 2. So again, we want gradient and point. If we already have x equals 2, shove that back into f, getting your y value. Point acquired. Next up, we need the gradient. If we have just f of x, that means f dash, and then shoving in the x coordinate, getting you your gradient. What we're going to do is take that gradient and chuck -1 on top of it. Now when we plug it into our normal line equation, it's -1 divided by 4 rather than just 4. Everything else rearranges exactly the same. What you'll find often is that you get fractions in your answer rather than whole numbers, which is less pleasant, but not too bad. That's tangents and normals. Any questions there? Awesome. So we do have some CAS shortcuts that you can use when it comes to your Tech Active exam. These are the CAS tangent line and the CAS normal line. So if we have a look at where both of those are located, they'll be located in the calculus menu. So if I pull one of these open, oh, I'm still in degrees mode, that's not great. Menu 4, and then if you look at the very bottom, 9 and A are tangent line and normal line. I'll do the normal line first, just because that's where the PDF is currently looking. The syntax is function, comma, x value. So in this case we have the quadratic of x squared. You do comma x. So for instance, if you had like y squared, you do comma y. It's just basically telling you, kind of like how you do comma x in a solve. You're telling the function what the variable is. So x squared comma x, and then comma the x value at which you are taking the tangent or normal at. If we then go ahead and hit enter on this, it'll write the exact same thing that I wrote except backwards, because it just likes to default put a positive value at the very beginning rather than do a y equals mx plus c. And then for tangent line, the syntax is again identical. X squared, comma, x, comma, 2, and you now have the tangent line at x equals 2. Fun thing as well that can help, you don't need to put a actual x value, like a number, in there. You can put a variable, or rather a constant is probably more appropriate, and this ends up being decently helpful for extended response questions, because, and we even saw a kind of example like this already, which was like we had the point a, x equals a, in our example 2 on the screen share if you have a look. Basically you could get the generic tangent line for this example, so let's have a look. Right? If this was like a Tech Active, for instance, we're trying to find the tangent to f of x at this point. What we could do is we could basically plug in exactly that related information. So instead of having our x squared there, we could have 2e to the 3x. 2e to the 3x. And what comes out, it might not look like it, but that is a linear. That is the generic tangent line. So as soon as you go through your procedure of finding a equals a third, if I go ahead and do a quick few definitions here, define this as a function, and then let's assume that we've figured out that a is a third using the same procedure. If I then reprint h of x, you'll see that it fully simplifies down to 6ex, which is exactly what we were expecting it to do. So this is just one way that you can use them. The other place this comes in handy is Unit 3.4 when you're doing, well, I think, Unit 3.4 does Newton's method for the first time. I think that's correct. Anyway, Newton's method is all about these tangent line things, and oftentimes doing something like this might help for those kinds of questions. But okay, that's tangents and normals. The next bit up are the stationary points. Actually, do we want to do any questions first? How much is here? It's just stationary points and nature of stationary points. Nah, it is a bit dense. Okay, let's do a few live examples. So just basically solving tangent and normal isn't really too complicated. We've already seen a few examples of just getting them, just with the basic information of point, gradient, so on and so forth. Let's see if we can maybe start with a more complicated thing. How complicated is this? We got a function. Okay, prove that tangents at P and R are parallel. Yeah, okay, this is reasonably more complicated. Okay, so we have our function. It's a polynomial, it's a cubic more specifically, and all they essentially did was label all the x-intercepts as different letters P, Q, and R. And the question is not necessarily even asking you to find the tangent line here. It's saying to prove that the tangents are parallel. So that doesn't necessarily mean you have to solve the full tangent line, although it can be achievable. To prove things are parallel, first we need to understand that parallel just means that they share the same gradient. And as soon as gradient-related information comes into play, this is where the derivative starts becoming quite helpful. So for this particular question, first up, defining our function will be nice and handy. X minus 2 times x take 3 times x take 4. Okay, it was just ascending. And might as well get the derivative as well. D dx function. And we don't really care what it actually is, just that we have access to it. Cool. So to prove that the tangents at P and R are parallel, what we want to do is prove that the gradients at P and R are parallel. So if we look at the coordinates P and R, those are x equals 2 and x equals 4 respectively. So if I chuck those into our gradient formula, I should expect that both those x coordinates have the same gradient on my function, which they do. They both have a gradient of 2. That'd be the most fastest way to go about it. If, however, you see the word tangent line, you're like, yep, I'm just going to solve the tangent, that's perfectly fine too. What you would do in that case would be function, comma x, comma 2, and then function, comma x, comma 4. And when you look at your two tangent lines, you'll see that they have the gradient of 2, right, for the m spot on your linear. So in either case, it's perfectly fine. In a tech free, you'd obviously want to just stick with the derivative. In a tech active, it's actually marginally faster to do tangent line, because if you see what I had to do, I had to define the derivative first and then plug in the 2 spots. This is one less type. Maybe it's just, it's marginally different. But yeah. Any questions about that, let me know. Otherwise we'll move on to part B, which is at what point does the normal to the curve at Q cut the y-axis. So this is now the normal, which means, yeah, Tahan?
Yeah, just want to clarify something. So about the tangent line equation,
Yep.
like what the values in it are. So I can see, so h of x is that original value. I'm looking at what's on the CAS.
Oh, yes, sure.
So
The CAS
h
one.
of x, yeah. So h of x is that like original equation, and then
Yep.
what do the x and the 2 symbolize?
So the x is kind of like when you do comma x on a CAS solve, it tells you what the variable is of interest. This is because, if you have like ax squared, for instance, it doesn't know if a is the variable or x is the variable. You're just telling the CAS which one to care about. And then the 2 and the 4 on both of those are the x coordinates at which you want to find the tangent line at.
Okay. Yep. Cool. Makes sense.
This is also mentioned. Okay, yeah, I guess it's a bit ambiguous of the syntax here. Yeah, cool. But yeah, that should hopefully clarify things up.
Yep. Thanks.
Yeah, no worries. Okay, part B. At what point does the normal to the curve at Q cut the y-axis? Or in other words, it's just asking what's the y-intercept of the normal line. Well, to achieve that, we need to find the normal line first. In a tech-free way, it would just be a matter of, expanding out this polynomial, finding the derivative, shoving in derivative x equals 3 into that to get the gradient, -1 divided by it for the normal, and then plugging in the point that you already know. In the interest of time, we'll just be using the CAS equations instead. Whoops, I am muscle memoried into my probability stuff apparently. But okay, so normal line instead of tangent line. Syntax is functionally identical. Function, comma, x, comma, in this case it's q, so q is 3. That gets us the normal line of x minus 3 rather. And so the y-intercept of that would just be minus 3. Right, x equals 0. Any questions there? Okay, let's see if there's another one. Probably something like this is the other one that's worth doing live. Let me just check these real quick. Find equation to tangent, find coordinates of the point where the tangent meets the curve. I'll just briefly touch on this one. At what points on the curve is the tangent parallel to this? Just rearrange this back to y equals mx plus c, and then it's the exact same question as 5a. That's all that you really need to worry about for that. But this one, we've done an example of it. Let's go ahead and, well, I mean, at least something similar. So let's have a look. For the curve with the equation of the quadratic, show that this is the equation of the tangent at that point. Cool. So a bit different. This time they've actually given you what the generic tangent line is ahead of time. Remember, a is a constant, so you've got mx plus c. Basically prove that if you do the tangent here, you get that. So since it's a show that, we're going to have to do some working. So let's get writing. Okay, so how do we find a tangent? We need the point and the gradient. The point is already given to us, even if it's not fully numerical, so we don't really need to do anything from that aspect there. What we do need is the gradient. We have our function, so whenever we have our function, we can always find the gradient of said function by finding its derivative. So if y is equal to x squared plus 3, which it is, then that means the derivative y dash, or dy dx, is therefore 2x. From here, the point that was mentioned was a comma, I mean it's essentially just a comma y of a, really, that's all it is. The derivative only cares about the x value. So y dash of a therefore gives us 2a as our gradient m. So when it comes to the, you can do y equals mx plus c if you want, and that's just a bit of a solve, or you can do the y take y1 equals mx take x1. And that way all you're doing is plugging in the y coordinate, the x coordinate, and the gradient, and then just doing a bit of rearranging. It's pure personal preference at that point. My personal preference is the gradient point formula, so we're just going to do that. Y take y1, so that's going to be our y of a, which if we look at the actual book was just a squared plus 3. Y take a squared plus 3. Remember, it's minus the whole point, right? So this is maybe one disadvantage of the gradient point formula. You have to be very mindful of when you're doing your substitutions. Equals our m gradient, so 2a x take x1, where x1 is our x coordinate of a. Now all we're doing is rearranging. So that'll be y minus a squared minus 3 is equal to 2a x minus 2a squared. And then finally, we're just getting y on its own. Yeah. Y equals 2ax, plus a squared to both sides is going to bring this one back down to just minus a squared, and plus 3 to both sides is going to get us that. If we have a look back at the question itself, we have exactly written out what we're supposed to. Y equals 2ax minus a squared plus 3. This is the generic tangent line. So for instance, if I wanted to find the tangent to my function at x equals 2, all I'd have to do is plug in a equals 2 into this, and I would get the tangent line, because I've already done basically all the algebra ahead of time, because remember that a was a stand-in for essentially just an x-coordinate. Any questions there? Cool. Next up, hence find the coordinates of the 2 points on the curve, the tangents of which pass through 2, 6. Okay. So to get a nice visual maybe, we have our axis. The quadratic is pretty easy to draw, it's just x squared plus 3. And the tangents need to pass 2, 6. 2 and... Okay, hang on, if I just do a quick math here, 2 squared is 4, 5, 6, 7. Okay, so it's actually a little bit below. Wait, what am I saying? X equals 2 needs to be a bit further, and needs to be a touch below the quadratic. Let me just double check that again. 2 squared is 4, yeah, 5, 6, 7. Cool, okay, so as far as the visual goes, we're looking for basically 2 points on this curve where if I take tangents at them, we'll pass through that point. So based on the visual, just eyeballing it, if I took a tangent there, it'll pass through, and if I took, let's say, a tangent there, it'll pass through. Obviously not great, I'm just sort of eyeballing it, but this is just to get an idea of what we're trying to achieve. We're trying to achieve what's this point and what's this point. So, the nice thing about having this is that there's two purposes, or there's two ways you can use it. One is if you already know what these x coordinates are, you can shove them in, and then that'll give you the full y equals mx plus c. Alternatively, if you know a point that this linear needs to exist on, which it does, right, which we do have, 2, 6, that gives you a replacement for both the x and the y, which therefore leads you to solving for a. And if we solve for a, what we'll find is we'll get two solutions, and then once we have our a, we can go ahead and plug it back in to get those equations. So to reiterate on that, because this is a generic tangent line, and these drawings are themselves tangent lines, any point that they pass through should therefore be able to be substituted into that function, which is what we're doing here. We know that both of these are forced to pass through 2, 6, so we're going to go ahead and plug in 2, 6 into this, and then solve the two solutions for a. So that's y equals 6, x equals 2, minus a squared plus 3, and we're just going to solve for a. 6 equals 4a minus a squared plus 3. We now have a quadratic, so let's go ahead and do that. A squared minus 4a, and 6 take 3 for 6 minus 3 for 3. From here, personal preference on how you want to solve the quadratic. This one should be factorizable, minus 1 and minus 3. A minus 1, a minus 3. Yep, it's going to multiply out to give positive 3 and add together to give negative 4. That's going to give you a equals 1, a equals 3, which reasonably lines up with the drawing. Yes, I've done a bit of a shit quadratic, so it looks like the 3 is actually behind the 2. That's more of just my drawing rather than anything else. And so yeah, having a equals 1 and a equals 3, what that means is the x-coordinate of both of those points is 1 and 3 respectively. We don't just want the x, we want the y as well. And since those exist on... Actually, yeah, you can do this in a couple of different ways. You can plug into the linears themselves if you want. Probably easier to just plug into the quadratic though, because both of those points clearly exist on the quadratic, whereas since you've got two separate linears, you'd have to be plugging into two separate equations there, which is not as good. So let's go ahead and use the quadratic, which, as a reminder, was x squared plus 3. If we plug in the a equals 1, so x equals 1, we have 1 squared plus 3. And that's going to get us to point 1, 4. Lastly, plug in the a equals 3, or the x equals 3. 3 squared gets you 9, plus 3, 12. So that's going to give you 3, 12. These are your final answers. 1, 4, 3, 12. You can go ahead and also validate that as well. If you're tech active, you can just, what would you do? I guess you just solve the tangent lines on them manually. At x equals 3, at x equals 1, and see if you plug in x equals 1 you get 4, if you plug in x equals 3 you get 12. That should be what happens. It's probably the hardest question in the chapter section. Obviously there'll be different stuff in the external response, but for now this is just an overview of chapter related stuff. Alright, that's about it for tangents and normals. Any questions or clarifications so far? Alright, next up, stationary points. Again, something we've done quite a bit, so I'll keep it at a fast pace unless you guys would like me to slow down. Feel free. Okay, stationary points. The whole idea here is it is a point in which a function is either turning or essentially momentarily stationary, or in other words has a gradient of 0 at that spot, perfectly flat. If you were to like try to rest or try to find the gradient at that spot, the gradient would come out to be 0. As far as terminology goes, you've got local maxima, which is for maximums, local minima, which is for minimums, and stationary points of inflection, which we'll discuss in a little bit of the nuances there. Your inflection points, or your stationary points of inflection, are just momentary spots first found on the cubic where you have a gradient of 0. There is a difference between a point of inflection and a stationary point of inflection. These are points of inflection. So points of inflection are just spots where the graph wobbles, essentially, right? It goes from concave up to concave down, or from concave down to concave up. You don't have to worry about those terminologies, just, going from rising to falling-ish, or falling to rising. That's the rough idea. That's what an inflection point actually means. Looking at the steepness at those spots, it is clearly not 0, right? It is rising. And so a stationary point of inflection will have a gradient of 0, whereas a point of inflection will not necessarily. Because that's something that has come to be interesting in a couple of questions. Question, will local maxima, local minima and maximums technically count as points of inflections? No, because you're not going from concave down to concave up or vice versa. This entire curve is concave up and this entire curve is concave down. There's no spot where it changes in its concavity, so to speak. Like you can see how basically, actually let's think about it in terms of like gradients, right? Gradient is decreasing this entire time, for this entire duration. Gradient is increasing for this entire duration. Maxima on cubics, as in like the ones that have two stationary points. Yeah. How would it work there? Yeah, so those would, that's why, in fact, like the cubic is pretty much why they are called local maxima and local minima. It's because it's not actually the true max or the true min of the function. So we have a stock standard cubic with the two stationary points. Like, this is the maximum. Obviously it shoots off to infinity if you have no domain restriction. And you know, down here is the minimum. Local maxima, local minima are these spots here. Alright, it's the turning points. Now, the same the same description that I gave earlier is still valid here. For this entire duration around the point, that's always concave down. The gradient is decreasing both left and right of the point. It's going from steep up to steep down. Same thing here. The gradient is going from steep down to steep up, either side of the thing. What you do have is another inflection point where it goes from concave down to concave up. And it's at that point where you have an inflection point, but not necessarily a stationary point of inflection. You can see that this one has quite a trend going downwards. It's only the x cubed, the basic cubic, I'll just draw it off to the side, where, okay, I drew that one a bit drastic, but where it has an actual flat point there. And so yeah, it's not about the, like the wobble is all about your inflection points. So that's going to be here and here. And more so the, yeah, thinking about things in terms of, you know, whether it goes from concave down, concave up, or vice versa, that's when you get your inflection points. For the other stationary points, it's all about gradient zero, essentially. And, you know, they're fairly obvious to spot. You just look and say, yep, that's a hill, awesome. Cool. If there's any further clarifications for that, let me know. Otherwise, we'll continue. Okay, so how do we actually find stationary points? At the very beginning of this, I mentioned that stationary points have a gradient of 0. As soon as I say the word gradient, literally ever, in any context, you're going to be finding the derivative. Like, there's very few cases where you won't be finding the derivative as soon as gradient-related information is given to you. The fact that stationary points have a gradient of 0 just means that when you do find a derivative, you set it equal to 0, because that is forcing gradient to be 0, and because you're forcing the gradient side of things to a set value, when you solve for x, you are solving for the x locations, that would give you gradient of 0, which by definition are stationary points. So it just said, you know, find the stationary points of this cubic, you find the derivative, gets you down to a quadratic, set it equal to 0, in this case you get two solutions. That is not the full point, that is just the x coordinate, so make sure you then go ahead and shove those back into the original function. Not the derivative, but the original. It's a very easy mistake to plug it into the derivative by accident, and then you'll be like, oh shit, the y coordinate's also 0. No, not quite. Make sure you plug it back into the original function, because that's the one that has x and y. Derivative has x and gradient. And yeah, I mean, we basically have the exact same drawing I drew, more or less, just with actual numbers now. Right there would be an inflection point, but finding that's a bit challenging. The other kind of question isn't necessarily about finding stationary points, it's just using stationary point information to help you solve other related things. One of which I can solve is an unknown. So we have a curve that isn't fully known, you've got an a involved in there, but we're told that it has a stationary point at x equals 3. The information provided there is in two parts. One is that it's a stationary point, and one is the x coordinate of the stationary point. Stationary point was mentioned, so derivative is really, really helpful. So let's just start with that. This is now a statement that says gradient is equal to 2x minus a. So if you have gradient, x or a, you can solve for the other thing. We just care about a, so as long as we can plug in an x and a gradient, we'll be happy. There's our x, and there's our gradient. X is 3, stationary point means gradient 0. So we plug in 0 into that spot, which I've unhelpfully rearranged a little bit. So gradient goes to 0, and the x goes to 3. Any questions? Let me know. Because we're going to go into a really complicated looking question. In fact, this is not Unit 1 and 2 at all, because this technically requires a product rule. Let me have a look. Do they have a Unit 1 and 2 equivalent of doing this? Doesn't look like it. Yeah, I think we'll just skip that then, because product rule is not Unit 1 and 2 related. But okay, so that's on finding stationary points and a little bit of application on how you can use it to solve adjacent questions. The challenge of what we've just discussed is that gradient 0 finds stationary points, yes, but it doesn't tell you what type of stationary point you just found. The textbook will cover a long-winded way of determining what type of stationary point you found. It will ask you to create a gradient table, which essentially just means find a derivative, set it equal to 0, thus finding your stationary point, and then pick two values either side of that. So let's say you had a derivative equals 0 and you got... Okay, well that's a bit complicated. Is there a simpler one? No? Okay, cool. I'm just going to make one up then. So if I start drawing one out, let's say we did f-x equals 0, and that gave us x equals 2. We just had one stationary point. When we set up our table, we put the stationary point x coordinate in the middle, and we draw a little flat line that represents the flat point on your function. From here, I'm just going to draw out the rest of the grid. The idea is that we say, okay, x equals 2 is a stationary point. Awesome. If I pick a number less than that and a number greater than that and evaluate the gradients at those spots, I should be able to therefore get a rough idea what this curve will look like. So, you know, one left, one right, or you can be a bit more strategic and choose x equals 0 here, because that's usually easier to work with. Either way, basically it means evaluating f dash of 1, and let's just say you get a positive number. This one would be evaluating f dash of 3, let's just say you got a negative number. What that would now mean is, because positive number means positive gradient, that would mean that your gradient, your slope, is rising. And if this one is negative, that would mean that your slope is falling. And if you look at the curve that's created from that, wow, that's a local maxima. That's what the book is suggesting that you do. You essentially find the derivative, set it equal to 0, which is something you have to do anyway to find your stationary point, and then it's suggesting you just plug in 2 more points and then draw up a table. There is another way, which is referred to as the double derivative test. It is a decent amount faster, especially if your derivative is something that is complicated, like a big function, not necessarily so easy to evaluate, and especially if the stationary point is at a shit spot on it. Like, you know, if you've got like a 4 on 3 or whatever, evaluating numbers either side of that. Well, not necessarily, actually that's a bad example. Maybe a better example is if you look back at the screen share, like if you have 2 stationary points, you now have to evaluate even more points either side of those to get what's what the net curve sort of looking like. And so a decently, maybe even just slightly faster way of going about things would be the double derivative test. Purely optional, you don't have to use this, you can use the table if you want. It's essentially just a quick criteria. The double derivative of a function just means finding the derivative of the derivative. So if we had the derivative is x squared minus 3x, back on the screen share, then the double derivative would therefore be just the derivative of this. So the x squared becomes 2x, the 3x will become 3. Then all you do is, so long as you already have your stationary point, which you will in either case, you just take the x coordinate of that stationary point, shove it in there. If you get a negative, it's a maxima. If you get a positive, it's a minima. If you get 0, it's a point of inflection. That's pretty much it. It's just a quick lookup. So if we have a example here, the reason why this is marginally faster is because when you do double derivative, like each derivative that you do steps down the complexity of the function that you're subbing into rather rapidly. So for instance, if your derivative was 3x squared minus 12, which it is in this case, then double derivative just gets you down to a linear. So rather than solving a quadratic, you're now solving a linear. You imagine starting at a cubic, going down to a quadratic, that's drastic. It'd be a massive time save to be doing that. But okay, so we have our double derivative. What are we doing with it? Well, we have our stationary points, which we found earlier. We're just going to shove in those x coordinates and evaluate what comes out. This is a positive number, this is a negative number. You don't even necessarily need to solve anything beyond that, right? Like if you can just see that 6 times 2 is a positive number, you don't need to write 12, you just say positive. Awesome, got it. If you can see that this is going to come out to be negative, just write a negative. Because the only thing that matters is whether it's positive, negative, or 0. But okay, so let's have a look. F dash dash of 2 was a positive number, it's 12. So if we look at what we say when it's positive, so greater than 0, that means that we must have had a local minimum. Awesome, so that means that point is a minimum. This one, if we look at what I evaluated to, was a negative. Using our lookup table, that therefore means maximum. And sure enough, if we look at what both of those were, negative 2 we said was maxima, bang. Positive 2 we said was minima, minima. Yeah, just a quick lookup. That's all it really ends up being. Any questions there? It's basically a personal preference thing. If you'd like to memorize the 3 little things, you've got that. Otherwise, you're doing, in the worst case scenario, I mean, geez, look at some of this stuff. Actually, what is this? Is this even relevant? Yeah, in the worst case scenario, you're just subbing points into a derivative, and hopefully that derivative isn't too bad. Cool. Okay, we're running out of time. How are we doing for this example? How long's this? Yeah, that's chill. Okay. So one of the things we don't practice much is analyzing graphs for gradient-related information. In this case, we're essentially looking at the opposite. We're given our derivative, and based on the derivative's graph, we want to determine the nature of the stationary points of the original. Alright, so we're not necessarily looking at here and get out of the way. Here. Those will be the stationary points of our derivative. We want to figure out the nature of the stationary points of f. So, how do we do it? This is where double derivative related information can help. But you need to be a bit more nuanced in understanding like why this criteria is the way it is, and I'm pretty sure we're going to explore that. Let me have a look. Yeah, we are going to go through that. So we're looking for double derivative here. So, because we just discussed that double derivative helps us find the type, the nature of a stationary point, the double derivative graph should be fairly helpful. So that becomes something we'll be looking for. So when it comes to creating that from this graph, just like how we go from f to f dash with any given graph, it's the same procedure to go from f dash to f double dash. which means we start by looking at the turning points of this function, which then become the x-intercepts of double dash. Right? Because whenever you find derivative and set it equal to 0, you find stationary points. So derivative being 0 forces y equals 0 on your derivative. Just eyeball it, right? Doesn't have to be too specific if they're not giving actual numbers. From there, based on those turning points, you are now splitting your graph up into those equal sections and essentially identifying the net gradient in each of those sections to therefore draw out what that would look like. We discussed this already when looking at the f of x to f dash. It's literally the exact same thing. We're just going down a level. So if we look at section 1, since it's net positive gradient going upwards, it means that you start with positive y values on your double derivative, because, well, that's how it works, right? Derivative of one graph means the gradient of the original. From there, next section is going net downwards, final section net upwards. Downwards means negative y values, upwards means positive y values. We can see that we got a quadratic, which should make a decent amount of sense considering that we started with a cubic. If you try to find the derivative of a cubic, you should get a quadratic. That's another way that you can validate whether what you did was right. Why do we care? Why don't we just find the double derivative? Well, we can now use this to, again, use the whole positive negative 0 thing to figure out the nature of the stationary point. So if we look at our f dash, any x-intercepts on that are stationary points of the original. Alright, so there's a stationary point at -1, +2, and +3 of the original graph. If we look at where those now correspond to on our double derivative, we can see that we get a positive number for the x equals -1 thing. It's a positive y value. We get a negative y value for this one, and we get a positive y value for this one. Again, looking at our criteria, or I guess I'm just, assuming you've already seen it. Positive means minimas, negative means maximas. This might be something you'd want to either rewatch or give a read over again. Not necessarily because it's something new, but more so just because we're throwing more dashes in the functions and it just makes it look more complicated. In fact, actually no, that's not really giving it full justice. We are technically looking across 3 separate functions. We're solving things to do with f of x, and we had to get all the way down to f dash dash x to figure it out. So yeah, definitely give this one maybe another read. I had to kind of rush the explanation a little bit just to make time on that. Alternatively, I can stick around for a little bit should we need me to clarify anything. If not, thanks for coming.
Hey Chris, I just had a quick question related to prob.
Yep.
Yeah, what was the CAS shortcut to get factorial again?
Ah, yeah. Factorial's in the. It's the one opposite the pi menu. It's here. The question mark thing.
Wait, can't see.
So it's like near the G. It's got the question mark and the exclamation mark.
Oh, okay, yeah. And then, okay, yep, I can see that now. Cool.
Easy.
Awesome. Thanks, Chris. Have a good night.
No worries. You too.